We will continue our discussion on pushdown automaton. When we discussed finite automaton, we said the class of languages accepted by finite automaton, one can describe something called regular expression. Such languages are called regular, and you can come up with a transition diagram, transition function. One can also describe this using something called grammars. In particular, for finite automaton, one can express the language accepted by finite automaton using regular grammars. Let's see what are grammars, and similar grammar can we come up with, can we describe for pushdown automaton. So just like natural language, these grammars have alphabet. Then there are production rules. So grammar G consisting of set of non-terminals and set of terminals, something called production, and start symbol. S represents start symbol. This represents production. This means terminals. This means non-terminals. This is analogous to the way we describe natural language statement. For example, we say India is a country. If you look at a statement, this statement, S is a statement. S can be written as noun phrase and verb phrase. Fine. And this verb phrase, you will find a verb in it. Again, there will be a noun phrase in it. Inside that, you will find an article and so on. So, which means you can look at it this way. Further, this verb phrase consisting of verb and noun phrase, and again in turn this will have something called adjective and then noun. For example, if you look at this statement, India is a country, you can see that when you say India is a country, this can be seen as noun phrase and verb phrase. And this verb phrase has got three components consisting of verb and an article followed by a noun. So which means you say statement S implies noun phrase followed by verb phrase, and verb phrase is consisting of verb, an article followed by a noun, meaning verb phrase consisting of verb and a noun phrase, and in turn noun phrase consisting of an article followed by a noun. Okay, so we just like this, we want to come up with a similar production rules grammars for finite automaton. These rules are called productions, So the natural language statements are precisely collection of words, but it is not collection of arbitrary words. They are combined using certain rules. The rules are given by grammars, in particular production, correct? So we don't associate the words just like that, right? We say this is how it has to be. We say if it is a noun followed by there should be a verb, correct? And followed by maybe an article followed by a noun. So which means we define certain rules. According to the rules, we frame sentences and we combine sentences to get paragraphs and so on. And so the rules are defined by grammars associated with the natural language. On the similar line, we have a language called regular language accepted by finite automaton. Can we define grammars? Can we say this is how the strings are formed? This is how, just like how sentences are framed using subwords or words, can we say how are strings formed? Can we come up with the production rules that will say if you follow this, this string will be generated, and such a string is part of the language. And if a string that is not generated using these rules, then they are certainly not part of the language. So similarly, if you come up with a statement which is not respecting this grammar or production rules, we say such a statement is grammatically incorrect. We don't accept such statements. On the similar line, if you come up with a string which cannot be generated or which do not follow from the set of defined rules, we say such a string is invalid. Such a string is not accepted by the automaton. Correct? So, analogous to this picture, we want to come up with a grammar consisting of, this is the signature, something called non-terminals, terminals, productions, followed by start symbol. Usually, non-terminals, we use capital letters. For example, S, A, B, and so on. Terminals are basically our input alphabet. We use small letters A, B, C, and so on. And things that are part of sigma, they will appear here. Now the question is, how do we relate terminals and non-terminals? And the relation between these two is given by the production. And you may have many rules, correct? So you cannot directly start with an article, correct? And so which means you cannot say the statement itself just the article, the, a, okay? So which means the production rule says where exactly I should start, and that is given by the start symbol. The start symbol is also a non-terminal. So which means the production rule starting from the start symbol will be the very first production, and subsequent rules are generated out of the start symbol, correct? So keeping this in mind, let's explore regular grammars, and subsequently we will move on to grammars accepted by pushdown automata. Consider this automaton Q0. On reading A, we go to Q1. Subsequent A's we read here. When we read a B, we go here, and subsequent B's we read here. We know that the language accepted by this is A power n, B power m, and n comma m is at least 1, because we read at least one A and one B. So in some sense, this grammar is trying to come up with recursive rules. So with recursive rules, you can generate a base string and then subsequently using that you can generate one more string, some more strings, like that you start building the language itself. For example, if you look at the language, it has AB in it, and then it has got AAB in it, then it has got like this. Then you can have say 2 A's, so many B's, and so on. Now, can we come up with a recursive expression which will describe this infinite set? Just like regular expression, you come up with a finite way of expressing an infinite set through algebraic operations. On the similar line, here is an infinite set. Can you come up with a finite set of rules? Using finite set of rules, one should be able to describe this infinite set. So here is the way I describe the grammar. Let's kind of play with couple of examples and then extract a larger message. For example, I say Q0 implies A Q1 and Q1 implies A Q1, Q1 implies B Q2, Q2 implies B Q2. Since Q2 is the finite state, I include one more rule or production called Q2 implies this. Now, these are all my production rules. For this language, for this automaton, here is the description. G consisting of N, T, P, S. What are my non-terminals? My non-terminals are states Q0, Q1 and Q2. What are terminals? Terminals are the input alphabet, so A comma B. Production, these are all production rules. And where am I supposed to start? My start symbol is the symbol that is starting with Q0. Fine. Now, this infinite set is described using these finite set of rules. So, what is my claim? Strings that are generated out of these rules are precisely part of this, are precisely accepted by this automaton. If a string is not generated using any of this, starting from Q0, then we say such a string is invalid. Such a string cannot be accepted by this automaton. Let's understand how strings are generated. What is the simplest string? It is AB. Please note, you should always start from start symbol. I cannot start with Q1 or Q1 or Q2 or Q2. Okay. This is what I was referring to. You may find in a natural language article implies the. Article implies so I should not directly start from this. From a start symbol, you may be redirected to article. For example, the so and so. Okay. So that is different. But you cannot directly choose the production that says article implies something. So on the similar line, I should not choose Q1, I should not choose Q2, I should always start from the start symbol. So Q0 implies AQ1. Now I told you it is a recursive expression. So you can replace this Q1 with any one from this. So let me choose this. A implies BQ2. Again for Q2 you can choose this or this. Let me choose this. So this becomes AB epsilon or AB. So this is called derivation for the string AB. So to generate AB, here are the production rules. It says Q0 implies A Q1, then Q1 is replaced with B Q2, then subsequently Q2 implies epsilon. So we have generated AB. Supposing you want to generate this, again I should start from the start symbol. So Q0 implies A Q1. Remember, I need some more A's. So between these two, I'll choose this because it begins with A. If I choose this, then you won't be able to generate this. Then again, I replace this with A Q1. I still need one more A. So what I do, I say this. Now I need a B. So then choose a production that says B followed by a state. Now if you use this for Q2, then you will get one more B, but we are done. So choose this and stop. So this becomes this. So here is a derivation for triple A followed by B. So according to your requirements, you choose the appropriate production. You can clearly see that with this you get the first A. If you keep applying this, you get remaining A's. So which means one can generate A power n using this. Now from this I go here and then start generating the first B followed by remaining B's, and there is no relation between these two. So I write B power m, and with this we stop, and this says at least one A and this says at least one B. So you get to see at least AB is there followed by any string of the form A power n B power m. This is interesting. An infinite set has got a succinct representation using a recursive formula or recursive set of rules. We call it as production, and it respects a certain rules, meaning you have to start from Q0, and this is how you should apply, and it clearly tells you that any string that is present here can be generated using this. Similarly, anything that is generated out of this is part of this. In some sense, soundness and completeness is guaranteed through this argument. Fine. The other interesting part over here is, for a finite automaton, you see that if you look at any of these rules, and they have just this epsilon, this is also a terminal. You can include epsilon as well, and or it is a terminal followed by a non-terminal, terminal followed by a non-terminal, terminal followed by a non-terminal. Always you get to see a terminal followed by a non-terminal. Something, the production that you can get out of the automaton, you can observe this. These grammars, this production rule and this grammar, they are also called regular grammars. Fine. Now, similar to regular grammars which are associated with finite automaton, we want to know the languages accepted by pushdown automaton. Can we come up with an equivalent grammar? Okay, so that's our next objective. Maybe let's look at a couple of more examples and see how are regular grammars constructed, and with that we will get an intuition, maybe an idea to proceed further to discover a grammar for a pushdown, for a given pushdown automaton.